Hi, and what's up to you all pre-matriculants? Well, Dina is going to dance for us. It is a lovely Monday, our Triple M day. It's not a dancing day. It is a Mindset is Maths Monday. Well, Dina, you're going to show us some dance? Like,
no, I've got no moves. I'm sorry. You wasted them all over the weekend.
I saw you doing something. Well, I think I was just being... Well, how are you, Dina?
I'm doing very well, and I'm ready to help you out, grade 11s, with some trig equations.
Guys, you can see we're ready to help you guys, and I'm so excited that already I've done my job. I've posted the link notes on facebook.com/learnextra. So guys, it's up to you now. The resources are out there waiting for you. All you need to do is just to click on the links, the view link and the download link if you want to download them. And also we have the test yourself link, whereby if you fill in the right answers, all of them, or most of them, if others don't get them, you stand a chance of winning this awesome Casio calculator, proudly sponsored by Casio. I'll be announcing our last week's winner, so stay tuned, guys. But remember, we also have more maths, MO Maths, whereby if you go to momaths.org and log in with this code, which is 0JRN, you stand a chance of challenging yourself with other mindsets and get to see where do you rank, how's your understanding of what we're going to be doing today. So it's a cool app that you can get to do at the same time and watch us at the same time. So it's cool. During break, you'll be doing that. Over to you, Dina.
Thanks, AB. And let's get started by looking at what our objectives for the lesson is today. We want to really build onto what we have done over the last few weeks in Trig. We've looked at functions, we've looked at identities, we've looked at trig graphs, and today we're going to look at how to solve a trig equation. And they are really going to be simple equations. They're not going to be the complex grade 12 type equations. So hopefully everyone this week will not be saying, I haven't done this in class yet, but rather let's do it together, even if you haven't done in class, so that when you get to class, you're just that little bit sharper. Great. So we're going to define, first of all, what do we mean by the concept of general solution, which is used when solving trig equations. What do we mean by that term, general solution? And we're also going to be solving some simple trig equations. Oh, before we get there, we do want to challenge all those out there who may be feeling that they know it all. So here we go. Let's see if you know how to work with the following question. The sine of sine A is the same as the sine of cos A, but it's opposite to the sine of tan A. Which statement is true? So we have a function sine A that's the same as the sine of cos A, but it's opposite to the sine of tan A. So which one of these statements would be true? So I'll leave you to go and really reason this one out and see what you can do with it, and we will look at the end of the show if you have been able to get it. Right, so we now have a little summary about the section that we're going to be starting off with. We have, firstly, a statement, sine theta is equal to m, and that is often how we want to get our trig equations. So if we have like 2 sine, a little pen, we want to behave. If we have 2 sine theta is equal to m, then you will want to get sine theta by itself. So you always want to isolate the trig ratio is equal to m over 2. So we would isolate the trig ratio first, and once we've got that, then the general solution for sine is always going to be whatever angle you have found using your calculator, and the trig solutions will occur over 360 degrees. Now, grade 11s, you'll remember that when we worked with a sine curve, the sine curve repeats itself after every 360 degrees. So whatever ratio we get for 10, at 370 we'd get the same thing. So there's a repetition of values every 360 degrees. And so because of that, we're saying that there's not just one angle that is going to give you that trig ratio, but there will be other angles that when you add multiples of 360, whether we add 360, we subtract 360, those angles will also give us the same ratio. And we'll look at that a little later. Or theta is going to be 180 degrees minus the calculator angle plus this case 360. And we must always use the definition, not use, but we must always give the definition for k, because we want to add 360 or 720 or 1080. We want to add multiples of 360. This k is going to be an integer. It's not going to be a half, it's not going to be a fraction, it's going to be a whole number, but it could be a positive or a negative whole number. Okay, then if we have cos theta is equal to a ratio, notice how cos theta has been isolated, then in this case, the general solution is going to be theta could be the calculator angle plus multiples of 360, or the additive inverse plus multiples of 360, and k is an element of the integers. So these are standard formulae. They are mechanical in nature. If I get a ratio for sine, I get 2 formulae. If I get a ratio for cos, I get 2 formulae. Let's see what happens with tan. If tan theta is equal to m, then the general solution will be plus 180, where k is an element of the integers. And in this case, remember that the tan function doesn't require 360 degrees to repeat itself. It repeats itself every 180 degrees. So therefore, the tan general solution, or the general solution that arises from the tan function, is actually a periodic over 180, and we've only got one formulae. So that's really nice, because it's whatever calculator angle that you get. Now, where do these come from? Okay. If we have a ratio, if sine is positive, for example, then we know that sine is positive for an acute angle and an obtuse angle. So I think you can see that that's a calculator angle, and that's 180 minus the calculator angle, which will give you that obtuse angle. So quadrant 1, quadrant 2, that's how we speak about those terminal rays and where they are found. But if we had sine theta is equal to a negative ratio, then we would get an angle, a reflex angle in 3rd quadrant and 4th quadrant. And for those of you who've already worked with a calculator, actually let me show you. If we say, let's say the sine function is negative, and so let's make a negative a half, 0.5. First of all, get the function. First, the function to the -1 means you're going to find your angle. And let's put a 0.5. Okay. Let's see what angle has this Casio calculator been programmed to give us. Can you see it's been programmed to give us -30? Now, -30 is not an angle between 180 and 270, and it's not an angle between 270 and 360, but it is a negative angle between 0 and -90, which shares a coterminal ray with the angle in the 4th quadrant. So this calculator has been programmed to give me the 4th quadrant angle. If it gives me the 4th quadrant angle, then I'm only missing my 3rd quadrant angle. And my 3rd quadrant angle would be 210, which is 180 minus -30. And so I really like this formula, because if m is positive or negative, this formula holds true all the time. Now, grade 11s, I know there are many of you out there who have teachers who are teaching you, or you're working with books that are teaching you how to work within the quadrants. Nothing wrong with that. I'm giving you today an alternative, which to me makes a lot of sense, and it's quite simple in nature, because you use the same formulae no matter whether the ratio is positive or the ratio is negative. I am capturing the essence of my angles in the quadrants in a different way, but my formula is standard. The moment the ratio is negative, I'm not going to change signs of the reference angle and then say 180 plus 30 and 360 minus 30. I'm not utilizing different formulae to get to my end result. I'm using the same formula. So that's the benefit of this formula. Then with the cos ratio as well, whether m is positive or m is negative, we will always have that theta will be the calculator angle or the additive inverse of the calculator angle. So those will be my reference points. Now, if cos is positive, it will give me a quadrant 1, quadrant 4 angle, and if cos is negative, it will give me an obtuse, and it will give me the third quadrant angle. So it's really, really easy to be working with those formulae. Let's see how we capture this in a question. So if we had to determine the general solution, and I said to you at the start that we would look as to what is the meaning of this general solution. Okay, and for that, I just want another screen. Okay, let's just go down there. That's fine. Let's just go down here away from the question, and let's just say, if I have 2x plus 3 equals 9, and I say to you, solve for x, you're going to say to me that there is a one value for x that will make this statement true. So you say 2x is equal to 6, and you say x is equal to 3, and you say to me the solution is 3. Now, I don't say that x equals 3 is the general solution, because there is one solution, and that value will make the statement true. Now, if I say sine x is equal to a half, and I had to draw a quick diagram of my sine curve. My sine curve would be doing something like this. It's periodic every 360 degrees, and it continues to infinity. And if I say to you, where is sine a half? Here's my half, because my maximum for my sine is 1. So if that's a half, grade 11s, can you see that there is one solution over here? There is another one that is 360 degrees later. There is another one that is 360 degrees later. And then this graph goes to infinity. So I'm going to get more and more and more solutions. So when I write down that x equals 30, that is one solution. But it's not all of them, because I can get it wherever I've drawn these arrows. Okay, so that's there, and that's there. Wherever I'm getting x equals 30. So I'm not going to write x equals 30, and then it's also happening at 330, and it's also happening at 390. I'm not going to be writing all of those down, because they're too many. They go off to infinity. So what I say is I use maths, I use clever maths, to say, hang on, I'm going to say it's 30 degrees, but then I must add 360 degrees. Actually, let's do it like this first. I must add 360 degrees. So let's add on 360 degrees. But then I must also add another 360 degrees. Okay? And why you are studying mathematics is so that you can be most efficient with the process of description, of writing down, and being able to explain it in a concise manner. So you can see that if I'm going to keep doing that, because that's 360 degrees later, that's 360, and then the next one, and the next one, so I would keep writing that down. I think grade 11s, you'll see that the first term has got 360, the second one's got 2 of them, the third one's going to have 3 of them. So the clever maths is to say, hang on, all this process, I can condense. I've got a condensed version for this, and that condensed version is K360, where K is an integer. So like this, if K is 1, I'm adding 360. If K is 2, I'm adding 360 times 2. If K is 3, another 360 degrees. Okay. But then you're saying, ma'am, there is one missing. What about this one here? This one over here is missing. How do we describe this one? How do we describe those? Because those weren't caught by the blue set of solutions. So there's a whole lot of other solutions that are here. Now the pink ones, okay, remember that sine is positive if we have 30 degrees, but it's also after 90. Between 90 and 180, there's a solution there as well that gives me a half. And that value is 150. And it also happens every 360 degrees. So the difference between that solution and this one, and why we call this the general solution, is because, firstly, this is not a specific, there's not one solution only that makes the statement true, But this variable over here, which can change, and it can be any integer, this k here, it becomes a variable that allows you to generalize. Okay, so I can generalize, and I can say, listen, if I have 30 degrees and I add on multiples of 360, then I'm going to get all the possible values if you keep doing that to infinity. So the moment you have a variable in your solution set, you generalize, and hence you get your general solutions. That's where it comes from. I hope that's clear. If we didn't have a K360, if we just had one value like x equals 3 or x equals 30, then that would be one value, and that would be a specific solution in a solution set. That wouldn't be the general solution. So the general solution is it's like a formula. It's the formula that catches every blue solution, and it catches every purple solution. So all those angles here are caught inside this formula, and we can go off to infinity as well. Okay, so that would be our general solution. Now let's go and see what our question was. Okay, we had to solve cos theta equals negative 0,102. First thing you need to check, have I solved for the trig ratio? Is my trig ratio by itself? It's got no coefficients, it's got no terms. Good, we're good to go here. It's been isolated. The moment you've got that, you want to use your calculator. But grade 11s, I want you to be smart, and I want you to think about it. If your ratio is negative and you put it into the calculator, what kind of angle is the calculator going to give you? You mustn't just think, oh, this machine's going to enlighten my world and it's going to make things easier for me. The machine does not make something easier for you if you don't understand what the machine's giving you. So if my ratio goes in as negative into my calculator, what is the calculator processing to give me an angle back? What's it doing? And what will it give me? You must always predict that that calculator is going to give you an obtuse angle. Okay, so let's see if the calculator is going to do that. We take there, negative 0.102. What is it going to give us? We said an obtuse angle. Let's see. There we go. An angle larger than 90 degrees, and we have found that it is obtuse. So I'm happy with what it's giving me. When we come back after the break, we'll keep going.
Awesome, Dina, and a big shout out to all the mindsetters that are watching. Guys, we'll see you after this break. Welcome back, Mindsetters. Now, great news. I'm announcing to you guys our winner of the Test Yourself competition, proudly sponsored by Casio. And our last week's winner is Refilwe Chele. Congratulations to you, Refilwe Chele. Coming your way is this awesome, cool gadget that you want to have every day on your bag, because it is about to be exam time, so you're going to really have to need it and use it every day. But now, Mindsetters, for your notes, remember, you go to learn.mindset.co.za. We've got a fresh new website which looks so great. So guys, do check it out on learn.mindset.co.za. It's cool, it's fresh, it's colorful, it's alive. So check it out and let me know on Facebook what you guys think about it. And also, I'm looking at some of you guys chatting with me on Facebook. Here's a comment from Tabo Semenya, who's a regular mindsetter, saying a shout out to all the grade 11s from Muchubaba Secondary School, including Garabo Lihodi, who's just liked the page today. Welcome to the family, Garabo, and thank you guys for being proudly Mindsetters, and also tell all your friends to like our page, and let's learn more and learn extra. Another comment, actually, it's from Nonsi, saying, yay, it's maths time. I'm so excited and I'm paying full attention to the lesson. That's all you need, guys. For you to learn more and practice more with us, you need to pay attention. It takes that. But remember where to get your notes, and remember to chat with me on Facebook and on Twitter at LearnExtra. I've been reading some of the tweets, Dina, such as one from Rose Malefu, saying she's joining us today and she's enjoying the show. Guys, tweet us and let us know if you are enjoying the show with us. Later on, we'll also be telling you that when you do answer the right questions on the Test Yourself, you could be a winner too. So guys, make sure that you enter. Dina?
Thanks, AB. And grade 11s, I set those questions. They've been set with a purpose in mind, that you are actually watching the show carefully and looking for those little subtle things that I mentioned that are important, that are going to be in those questions. So listen very carefully. And also thank you that you are enjoying the show, but most importantly, tell us what it is that you're learning. I would love to know how it is that the show is inspiring you to learn something new, see something with fresh eyes, think about things alternatively, all those kind of things. That's what's most important, because if you can be taking these things into your examination, then that's what makes us here at Learn Extra really, really excited. Right, we left off with cos theta equals negative 0,102, and I asked you to first of all decide what type of angle we were going to get. And we looked at it and we said that every time cos is negative, the calculator, well, this one, because I'm using a Casio, has been programmed to give me an obtuse angle. And so therefore I'm getting a quadrant 2. So notice how well I must know my Cartesian plane, because I'm talking in terms of where the terminal array will be. Terminal ray in quadrant 2 makes an obtuse angle, so therefore I've captured that angle. The other angle that I'm missing is the third quadrant. But the way that I'm going to refer to that third quadrant angle is I'm not going to say 180 plus an acute bit. I'm just going to say it's the additive inverse, because the cos function is symmetrical about the y-axis. It's very important to know that. So if we had to look at the cos function, if we had our cos function over here, and I sketched my cos there, then I would sketch exactly a replica on this side of 0. Okay, so there's 0. So if my ratio is negative, look what happens, grade 11s. If my ratio is negative, okay, my calculator has been programmed to give me this value, which is my obtuse angle, which means that 360 degrees later, I'm going to get this solution over here. There's my period of 360. Oh, by the way, somebody asked why 360, why we add 360, because of the function's period. Okay, it's not, we haven't plucked it out of the air. The functions are periodic over 360. So if I'm getting an angle that gives me a negative ratio over here, 360 degrees later, look what's happening. It's repeating itself. It's exactly the same ratio. Different angle, same ratio. So the period of the function is where we're grabbing those multiples of 360. Period for tan is 180, hence the general solution will have k 180 degrees. But, and if I go this way, here's my green angle. Can you see, grade 11s, that these solutions are missing? Now, which quadrant is the solution in? Okay, there's my 90, there's my 180, there's my 270. So those are my angles in third quadrant. That's my positive angle in third quadrant. Here's my negative angle in third quadrant. So we talk about those two as being coterminal angles. So in your general solution, you can have that value, or you can have that value plus K360. It doesn't matter. And this afternoon, I'm telling you that I'm going to use this value because the calculator gave me this one. The calculator gave me this obtuse angle. And this one, because my function is symmetrical, this value here is going to be exactly the same as that value, but just the additive inverse. So if I get 100 degrees over here, this angle over here is negative 100, which makes this angle over here 360 minus 100, which makes that angle 260. So 260 and negative 100 will give me exactly the same terminal rate. That's looking at it in terms of a graph. In terms of a Cartesian plane, it's like this. There's my origin, and I will rotate an angle into the third quadrant, and there's the terminal ray. So this angle over here is this blue one. Okay, there it goes, blue angle, that terminal ray. This angle over here is this angle there, same terminal ray, hence the terminal ray tells me the size of the angle, the positive angle, the negative angle. I mentioned to you an example. So if this was, for example, negative 100, then this angle over here would be 260, because that 100, 260 and 100 give me 360. So negative angle, positive angle. I'm using this afternoon the fact that the calculator will always give me the green, always, to always be the obtuse angle, and I'm going to look at the additive inverse. So in this case, the calculator would give me that as 100. I'm going to choose to use that one. But grade 11s, there's nothing wrong with choosing that one. Some of you will say, oh, the acute angle will be 80 degrees, so you'll take 180 plus 80 and you'll say 260. To me, that's too much mathematics going on there unnecessarily. I would like to be able to work with my curve, be able to understand my curve, be able to understand my Cartesian plane, be able to understand how angles are formed, their definitions, where they're positioned, and how we interlink them to get these various solutions. So without knowing that, I can't really solve an equation in any academic way. Then you're just mechanically going through it, but you're not really thinking through exactly what you're doing. Okay, but this was just to explain to you how the cos function is symmetrical, and in our question that we've just done, the value wasn't really 100, it was, I think, 95, if you remember. But 95 is obtuse. It's got 2 digits, and we often think that 2 digits should be acute, but it's not. It's obtuse. So let's go and have a look what's happening. I would like everybody to write down general solution. Don't just write, often students say this, let's put it in green. They say theta equals 95, because that's what your calculator gave you. That is wrong, because remember, we are trying to find all theta, not just one of them. So I would encourage you to write on the side here, away from the equation, calculator angle equals, what did the calculator give us? 95,8 dot, 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 because we haven't rounded it off yet. We don't know if there will be any rounding off, so that's what the calculator gave me. So it's giving me what kind of an angle? It gave me an obtuse, and it's an angle in quadrant 2, if you want to talk about it. So I'm missing, there's my quadrant 2 formula, 95,8 dot, 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 just 3 dots, plus K360, or I want my quadrant 3, which I know my angles are symmetrical, so it's negative 95,8, that's my quadrant 3, plus K360, and you always have to tell that K is an integer. Now, if there was no further working, that would be your final answer, and you could have rounded it off there. I've taken the next step because it was 95,85. Let's just double check that. Yeah, 85. So rounded off to 1 decimal place would be 95,9 plus K360, or negative 95,9 plus K360, where K is an element of the integers. This is the general, it gives you that. Now, what I am not doing today is what happens when you are given a domain. Now, a domain will say something like, please only give me the angles between 0 and negative 360. Grade 11s, then it's very easy. Then you're going to go into the multiples of 360. You're going to substitute 1, 2, 0, and see which angles are in that domain. But you will never, ever start with a domain. You'll always start with general solution. So go from general to specific. Go from the abstract to the tangible ones. Okay, right, so that would be the cos function. How to deal with, very popular one and where people make mistakes, cos theta divided by 2 is equal to negative 0,102. How do we deal with this one? We would have an isolation of cos theta. There is a half here, so we would multiply by 2, so it's negative 0,204, and then we would go straight into the general solution. General solution would be theta equals second function, negative 0.204, and that would give us 101. So just very interesting to see how we have doubled the ratio, kind of, okay, even though it's a negative, but it went from 0,102 to 0,204, and the angle did not double. So there is no relationship between doubling the ratio and then also finding that something magical happens to the angle. It didn't. We went from 95 to 101. It's hardly any increase. So that was 101. And because that is our final answer, let's just round off. Comma 77, so it's comma 8. I did not do what I often ask you to do, which is to analyze. So it was a negative ratio. What angle are we expecting? Obtuse angle. We're happy. It's obtuse. And that's my quadrant 2. So where else will cos be negative? Quadrant 3, which is the additive inverse of that, because my cos function is symmetrical. So it's negative 101, comma 8, plus K360. So that means K is an element of the integers. Right. Then let's look at the sine, because somebody asked about sine. How do we get, I think one of the mindsetters asked, how do we find the second angle of sine? And I think the best way to show that is with a picture. Pictures tell a story. Okay, so my sine curve, if my angle is positive, my calculator is going to give me this angle. So if my ratio was positive, it's going to give me that one. It's obvious that this angle over here, because it's symmetrical about the 90 degrees, this distance from 0 is going to be the same distance as that is from 180 degrees. So if I take 180 degrees minus that value, I'm going to get the second one. So to answer your question about how do I get the second angle of sine, it's always the second angle in quadrant 2 is 180 minus the calculator angle. And then you will ask, will it be the same if the ratio is negative? And the answer is yes, because we saw in the first segment that if my ratio is negative, sine is going to give me the fourth quadrant angle. And if you say 180 minus negative 30, you would be getting a third quadrant angle when it's negative. So same formula when the ratio is negative as when it's positive. And that's what I love about this formula, is it doesn't change for the different cases. The case changes, the formula stays the same. Really good. Right, so here, what's missing is that the ratio is not by itself. So sine A is equal to 0,785 divided by root 3. Leave your process steps in the calculation, because when you want to check your work, you want to be able to see what the processes were. Otherwise, it takes you a while to pick up where you may have gone wrong. So from here, we're ready to find the general solution. So we have A equals whatever the calculator gives us for that, 0,785. So we have second function sine, and we had a 0.75 that we were dividing by the root of 3. And let's get out of that, and let's close that. So what does that give us? It gave us 26,95. Were we expecting that, an acute angle? Yes, because the calculator has been programmed to give us the acute angle if it's positive. Whether it's sine, cos, or tan, you're always going to get an acute angle. When it's sine is negative, it's going to give us the fourth quadrant angle. When cos is negative, it's going to give us the obtuse angle. And when tan is negative, it's going to give us also the fourth quadrant angle. So we need to know the cases for the obtuse, for the negative ratios, what is being programmed into the calculator. So it's 26,95, which really rounds it up to 27 degrees. So A is 27,0 degrees plus, it says correct one decimal place, so you must show the decimal place. And then the sine is periodic over 360, or A equals second angle of sine is always 180 minus the calculator angle plus k 360, where k is an element of the integers. And that gives us, on your calculators, you can just go minus 180, knowing that you want the positive value of that. So that's 153. 153,0 degrees. So we get an acute angle and an obtuse angle. So here's my obtuse one, where if you go periods of 360 degrees, you'll get it over there, and over here you'll get that angle there. So it goes off to infinity. So the whole thing about the general solution is that your graphs continue, they oscillate to infinity. So unless your domain tells you to restrict your solutions, you're going to have infinite amount of answers. Okay. I think that was the negative ratio. What happens with the negative ratio? So let's do sine A as a negative 0,785. let's talk our way through this. If my sine ratio is negative, what angle has the calculator been programmed to give us? The calculator gives us this value here, gives us this quadrant 4 angle. So that is the first angle it gives us. The other angle that we'd like is the third quadrant angle there. And for that, I'm just going to use 180 minus this negative portion, which is the same. So that would be 180 minus the calculator angle. Just for this case, where this is the calculator angle, because it's negative. Okay, so general solution will be calculator angle, A equals, let's go and find it, sine of negative 0.785, and I'm dividing it by root 3. And what are we expecting to get? It's the same ratio as before, but it's negative. So we're not going to get 27 degrees. We're now going to get, awesome, negative 27 degrees. So negative 26.95, which we've rounded it off to negative 27. So it's negative 27, comma 0. Why is it 36 degrees? Because the periods of the function, or A equals 180 minus the calculator angle, and all that gives us 180 plus 27. So let's just take the negative of the answer, which is 27. So it's really 180 plus 27, which is 207. Or 207 plus K360, where K is an element of the integers. Right, so second angle, very clear here. It's always 180 minus the calculator angle. If the calculator angle is positive, this will give us an obtuse angle. If the calculator angle is negative, like in this case, it will give us the quadrant 3 angle, which is exactly where we want to be positioned. And then the nice thing is, grade 11s, you can take 207, you can take negative 27, you can substitute back in there, and you can see whether you're actually getting 0.785. You're going to get very close, because remember there was a rounding off to the nearest decimal. So, yeah. All right.
Thank you so much, Dina. Well, Monster, I think you deserve a break. You've earned it, guys. You've been focusing and chatting to me on the page. More info and more learning after the break. Welcome back, guys. Well, one last chance for you guys to go on moremaths.org. It's momaths.org, and your code is 0JRN. So log in there, and I have got a great comment about More Maths, Dina. It's from Lucas. I'll get it. It was somewhere there. But it's time for us to answer the challenge question, and I'll get that comment. Oh, it's coming. It's coming. Lucas actually is leading on More Maths, so he's so excited that through Mindset, he's now leading on More Maths. So guys, you've got a challenge. You've got someone that says, here I am, challenge me. Let's see if you can beat me out of the leading board.
My word, leaderboards in mathematics. When I was a student, the only leaderboard I knew about was the golf. You had a leaderboard in golf, or you had a leaderboard in the soccer league. But in mathematics leaderboard, that's fantastic. Lucas, keep it going. Come on, grade 11s. Let's challenge Lucas, and let's get on to my maths, and let's see if we can really try and get to that top spot, because that's where everybody should be, right?
Awesome. And my bad, sorry, it's Lucky Ratau.
Oh, sorry, Lucky, but you're very lucky we've corrected it. Okay, super duper. Right, so let's get back to the general solution. I want to make a comment. Some of you are asking about how do I find the reference angle. And I think over the last 40 minutes that you've been watching the show, I haven't once made mention of a reference angle. I've spoken about the calculator angle because that is what I'm using. I've shown you a new tool, completely new for some of you, that doesn't use the reference angle. It's actually just using the calculator angle. You've noticed that I've picked the angle as it was on the calculator. I haven't done anything else to identify where it's, which quadrant areas and how to use a reference angle. So I'm afraid if you want to use a reference angle, then you must stick to what your teacher's showing you, because I said to you right at the beginning, this is much easier than working with reference angle. So if the ratio is positive, the angle that the calculator gives you is always acute. And you can find the sine by saying 180 minus. You can find the cos by taking the additive inverse. And there is no angle for tan. There's only one angle. When the ratio is negative, I'm going to take the angle that the calculator gave me as my one set of solutions. So I'm halfway there. And the second set of solutions, for sine, I'm going to use 180 minus. For cos, I'm going to use the additive inverse. And there's no second solution for tan. So it's wonderful to be able to just use plainly the calculator angle. So if you go through the notes again and you see and you able to understand that, then that's fantastic. Unfortunately, don't have the time to also look at the reference angle option, because that is the most used one in South Africa, and I think it really doesn't tie in all the little bits of trig that we've actually been doing. So I prefer just using the calculator angle, much, much simpler. Right, so let's see. I think one mindsetter asked about why is this cos theta negative? It's negative because there was already a negative there. But I really want to look at tan because we didn't have a look at a tan example. So let's look at tan. Here we go. Here's an example where tan beta plus 5 is equal to 15,275. And remember to always isolate the ratio. So we're going to get tan beta is equal to 15,275 minus 5. So now I've isolated the angle with the tan ratio. Beta is going to be equal to, actually let's first write general solution. So the general solution, and a mindsetter asked why is it called the general solution. Once you go back into the notes, I've explained it very nicely there, just re-look at the notes. But general solution is a generalized version. It's a formula that is able to identify every single solution that that function has, and we sometimes only look for certain solutions if we are given a domain. Right, so the general solution will be that I would like to find my tan, the second function, tan. There we go, no. Okay, I'm not getting a second function. There we go. I get a second function. So 15 minus 5 is 10. So it's 10.275. So my angle is 84,4, rounded off to one decimal place. One of the mindsetters asked, do we round off to 1 or do we round off to 2? And for me, when I'm working with degrees, unless you're going to be going into engineering or architecture, you would maybe like 2 or 3 decimal places. But for us in maths, just pure maths, 1 decimal for angles is fine. If you take your protractor and you look at the markings, can you find 0,11 degrees? It's kind of virtually impossible unless you're doing it electronically and you can zoom in and you can find those angles. So I think 1 decimal place for angles is fine. But grade 11s, this is the golden rule. You always follow the instruction. So every test question, every exam paper, look for the instruction. What does the instruction tell me? Because if you miss the instruction, you're going to get penalized. If there is no instruction, then you would just round off to 1 decimal place and you would say so. You would say that you've done to 1 decimal place in view of the fact that there was no instruction. Okay, so the general solution, we're going to round off to 1. What did we have now? 84,4, there we go. So beta is going to be 84,4 degrees. And then, grade 11s, what is the period of a tan function? Every angle is repeated 180 degrees, or every 180 degrees we get a repetition of that ratio. So therefore, my period is going to be k 180 degrees, where k is an element of the integers. And I'm not even going to write down a second answer because I'm just using 180 degrees, and that will catch every single answer or every single angle in that tan function. So that will be my general solution. Now, what happens if the value is inside? Now, here's something very interesting. What happens if I have beta plus 50 degrees? So in the previous one, we had tan beta plus 5. So 5 is part of the ratio. It's not part of the angle. But here, the 50 degrees is part of that. Okay. Now, some of you are going to be tempted to saying, I'm just going to get tan beta, and I'm going to say that that's negative 15,275 minus 50. But that's a ratio. That is an angle. They're unlike, so we can't do that. So when there is this kind of an angle, which is actually a complex angle, okay, I'm going to leave it like that. I know some books will say, let's substitute it with A, and then we come back and solve for K later. Let's just leave it like that. It's part of that angle. As long as there's no coefficients and as long as there's no terms, then we're fine. So the general solution that we're going to find is going to be on beta plus 50 degrees. So I'm going to fetch the angle that has got that negative 15.275. So it's negative 86,3, negative 86,3 plus the period, K180, where K is an element of the integers. And then, once I've got my general solution, I now solve for beta. So beta equals that negative 86, which we're going to minus 50 from, and we get negative 136,3. Negative 136,3 degrees plus K180. You only have to say the K is an element of the integers once, so that becomes our general solution. Now, I know that mind-setters have been asking for clues, and Abram's loaded with messages on, oh, we cannot do this challenge question. Right, so I think it's time for the challenge question. AB?
Yes, let's do this.
Good. Right, let's see. Okay, let's go back to slide 1, where the challenge question is. There we go. And I'd like to ask you, mind-setters, what tools did you use to find the various signs of the terminal rays? You could have at your disposal a Cartesian plane, because a Cartesian plane defines the angles in terms of quadrants, or you could have had functions, and we're going to look at both, okay? So if I'm in the Cartesian plane, I would like to find out, okay, where is sine and cos. Sine is the same as sine. So sine and cos are the same. Okay, they have to be the same. You'll agree they're the same there, quadrant 1, but tan has got to be opposite. So tan is the same as those. It's not opposite. They're all positive in there. So it's not that quadrant. What happens in quadrant 2? Sine is positive and cos is negative. So they're not the same. What happens in quadrant 4? Sine is negative and cos is positive. So they're not the same. But what happens in quadrant 3? Sine is negative and cos is negative. So they're the same sign, but opposite to that of tan. And look what happens with tan. Tan is positive in that quadrant. So it was quadrant 3, which was between 180 and 270. So for those of you who use the Cartesian plane. If you used a graph, look how easy it was to use your graph. If I use my quadrants, and I sketch each graph in a different color, then my sine is going to go up to 1. It's going to go to negative 1, 0. So that's what happens to my sine function. My cos function goes from 1 through to 0, through to negative 1, there, and up to 1. So my cos function does that. Oops. Where are we going? And then my tan function, let's do it in pink. My tan function is going to do something like this, something like that, something like this, and something like that. So we see that here in quadrant 1, they're all positive, so it's not that quadrant. In quadrant 2, which is just the angles between these two verticals, sine is 1 and the cos is opposite, so that's not good. But in quadrant 3, sine and cos are the same, and tan is opposite. And in this quadrant, sine and cos are opposite. So you can actually see through the graphs that it was also quadrant 3. AB?
Thank you so much, and all the well done to all the mindsetters that have answered the challenge question correctly. I don't know if some were guessing, but it really worked for them. Thank you so much, Dina. We have to end it there, unfortunately.
See you next week.
Cool, and thanks to you guys for watching. And funny enough, Skumuzo is saying on Facebook, when Abraham goes, peace, ha ha ha, priceless. I love the show though. Well, it is that time, Skumuzo. I have to say peace with you guys. But otherwise, we love you guys, and we'll check you out some other time. Peace!